So I will introduce two major parts of our work, and I will bring out what's unique in our work and how it's separate from other work in the domain. So first area I want to mention is we have done a lot of work for cyber attack detection back in maybe from 1997 to 2007, about 10 years period. We did a lot of work there. And most of this work is actually captured in that first book I show up there. It just many part of the content in that book is actually are not published in journal paper or conference paper because we produce tons of work. I thought it's really, everybody know the journal paper publication process is a very lengthy, tedious process. We say, we'll just put everything in a book, okay? So if you're interested in some part I was talking about, that's the only place to find the detail. And I also have some other book in the data mining area, but that first book actually cover a lot what I'm going to emphasize today about what we have done for cyber attack detection. So there are two main distinct features in our work for cyber attack detection. Before we actually done our work, if somebody have done work for the cyber attack detection, there are two main techniques or methodologies. One is called signature recognition. So like that actually exists in a lot of commercial software for cybersecurity, like antivirus software. The idea is you capture the signature of virus or worm or cyber attack, and you store it in your computer. You try to match the signature against the ongoing activities. So that's basically we call signature recognition. So if you see the signatures, that found in your the database of virus signature, attack signature, that's signature recognition. And so this technique has been used a lot in commercial software for cybersecurity, for cyber attack detection. And another main approach is called anomaly detection. So that term may be different from anomaly detection in finance here. So anomaly detection in finance mainly talk about something basically outlier. How do you detect the outlier from non-activity? But back then, for cyber attack detection, there's a branch of technique we call anomaly detection. Similar idea. Basically, you define the norm profile, and any large deviation from that large profile is considered anomaly. Okay, so the key is define norm profile. But we don't see anomaly detection technique used a lot in commercial software for cybersecurity. And there's a reason for that, because there's some experimental system based on anomaly detection, but they usually generate huge amount of false alarm. And we know if you handle like 1 or 2 false alarm a day, you can handle it. But if you get like even 10 or 12 false alarm a minute, an hour, we just totally ignore that. So that's the problem. So that's actually the main challenge faced by anomaly detection technique for cyber attack detection. So that's I believe that's one main reason why this technique has not been put into commercial software for cyber security a lot. Okay. So then our work is different. We actually invent a new approach. We call it attack norm separation. So this idea is basically based on the observation. So let's say you collect computer network data. That's basically where you analyze those data to see if there's a cyber attack going on, right? If everybody in your mind imagine the data you actually collect or you're monitoring, it's actually a mixture of ongoing normal use activity and attack activity if there is attack going on at the moment. Everybody follow me? So let's say, every day we collect data from computer network system. There are a lot of normal user activity, right? Tons of them, basically. And let's say at this moment there's attack happening. And both attack and normal use activity produce effect on your data. So when you collect that data reflects the mixed effect of normal use and attack. And imagine, let's say, when you get this data with mixed effect of both type of activities, it's going to make both signature recognition and anomaly detection very hard to work. Because imagine, let's say, you have mixed data, right? You try to actually match your tag signature against this mixed data. Now, I like to use an analogy like the tag is like a signal you want to detect. And the normal use activity is like a noise you want to ignore for the cyber tag detection. Now, can you imagine on regular computer network system, the noise is a huge amount. There are a lot more normal use activity than attack data, right? You have thousands of users using the computer. So if you try to use signature recognition, like you want to use a signature to match against that data, where the effect of noise is tremendous. That signature, the signal is hidden there. It's buried in there. How would you be able to detect this signature? Very difficult. You see what I'm talking about? So if you think about it, it's really, your signal is buried in large amount of noise there. How would you be able to capture get that signature now? So signature recognition wouldn't work very well because your signature is buried in large amount of noise data. Now, if you think about anomaly detection, you want to basically, you try to match, see if the current activity is actually more fitting to your norm profile, or it has large deviation from your large profile. Now, remember again, that signature of the tag you try to detect, it's just a tiny little bit signal buried in large amount of noise. You wouldn't find, you wouldn't actually say, okay, this data is largely deviated from a null profile. It's probably fit right in there. So both technique will have problem to detect or capture the tag accurately. So that will affect the accuracy of both signature recognition and anomaly detection. So we actually recognize that problem. So we actually develop a new approach. We call it attack norm separation. To recognize, the data you get is actually a mixture of both normal use and attack activity. So that means you have to clean up your data before you can do an accurate job for detection. So the first step there you can see is we need to basically, in order to improve the detection accuracy, to reduce the amount of false alarm, you need to have both attack data model and normal use data model. You need both of them to work. If you think about the two previous approaches, signature recognition, you have attack data model. For anomaly detection, you have normal use data model. You have one of the two models, but you don't use both of them. So for this attack norm separation, you have to use both of them to increase the detection accuracy. So you have to define what is the attack model, what is normal use model. So that's, then once you have both model, then you actually, and the first step is that's define model of attack normal use data. Okay, and then we'll talk about how we actually define that later on. So that's the first step. And second step, you see, we try to actually, then we get your mixed data. We try to use your data model to remove the effect of normal use activity. Basically, we want to reduce the noise from your data first. So everybody remember analogy of signal noise? Basically, a noise I want to ignore, signal I want to detect. But the data I got is a mixture of signal and noise. So I'm going to use my noise model to remove the effect of noise from the data. Then the signal becomes more dominant. So I actually improve my signal to noise ratio after that step. Then once I improve my signal to noise ratio, the signal becomes more dominant. Then I use my attack model to match the signature. Everybody see the difference? So that's basically the new approach I want to mention, how we try to actually improve the detection accuracy, like reduce the false alarm. So that's the key idea here. And then and there's a specific technique we call Q-score statistic. Actually, we didn't invent the technique, but this is a perfect technique that actually works for this approach. I will show you a little bit more detail later on. So that's one unique feature of our work, which is different from other work like signature recognition, anomaly detection for cyber security. Now, if you think about the cyber attack detection, it actually has some similarity with the fraud detection in the finance industry. Okay, we'll get into that a little bit more too. And another significant difference is in the second bullet point, so a lot of time when we do data analysis, for cyber attack detection, fraud detection, we collect the data. We use the raw data, basically, data variable, and try to define the pattern and trend. Now, one thing we actually did, which is quite significant there, is we actually try to look into some mathematical statistical features rather than rely purely on the raw data variables. And there, I mentioned like 4 features we actually look into. One is probability distribution. So like everybody know about histogram. If you plot the data, the histogram, that's probability distribution. And we notice actually a lot of data pattern can be actually represented by the unique probability distribution. For example, for the computer network data, we see a lot of data pattern. Let's say you're looking at, for example, like the network traffic volume. That's one variable you can collect, right? And there are a lot of data pattern, like you have, small fluctuation, then suddenly spike, and small fluctuation, suddenly another spike. Okay, we actually see a lot of data pattern like that in computer network data. If you think about that data pattern and try to capture that using the probability distribution, you will end up to have what we call skewed distribution. Okay, skewed distribution is more like this. So there are a lot of data here, but there's a tail here, give you rare values, which actually reflect those spike. Okay, so there's other data pattern. Let's say I see a pattern, let's say we call step change pattern. So basically, normally, let's say it's one value, and it suddenly jump up to another value. For example, if you think about, let's say CPU usage time. During the nighttime, it stay at this low level. During the daytime, it jump up to another level. If you look at data pattern like that, you capture its a probability distribution, you are going to have what we call bimodal distribution, most likely. So your distribution will look like this with 2 bounds. So there's a lot of common data pattern. You look at the time series data pattern, can be actually uniquely identified using probability distribution. So we have actually invented some statistical tests which actually tells you which distribution you are having right now. So that's one feature we actually look into, which actually help us distinguish data pattern pretty well. And another is autocorrelation. We deal with time series data. It's like, like 1 autocorrelation, like 2 autocorrelation, those kind of things. And then descriptive statistics like a mean, variance, those are the descriptive statistics. And the wavelength signal strength, that's actually something I want to emphasize here. Because that's actually, I think it's quite useful feature. We usually think, wavelength signal strength is more like, the electrical engineer people deal with that a lot, telecommunication, basically. Signal, radio signal, it's all based on the frequency. So I remember back then when I was in college, I was actually computer science major, but we're required to learn a lot of math, like 2 year, a lot of math, first 2 years. And we do differential equation, 4-year analysis, whatever. And remember, I was computer science major. There are a lot of computer science major here. In your whole life career, have you ever used differential equation? Probably not, some of it. But most of us, we don't use differential equation when we do computer science work, right? Basically. So back then I say, why I'm doing this, really? Computer science is more like logic gate, those logic-based reasoning. So I don't understand it. And until some years later, I suddenly click. So I don't understand, why the frequency, if you work in the electrical engineer, frequency is a big deal there, I don't understand why the frequency is such a big deal. And it's just many, many years later, it suddenly clicked in my mind. Frequency is very important subject. Because if you think about, there are a lot of objects and even human behavior in the world can be characterized by frequency. So for example, let's say if you talk about me, let's say how many times I log on computer, maybe let's say 10 times a day, you look at another person, and who is not really much into computer, maybe 2 or 3 times a day. Then we're talking about the difference in frequency. Okay, and if you're looking at the space science, we try to detect new objects, new stars, basically. How do we do that? Frequency will be a very key feature. We find a new object which have different frequency orbiting, certain system. We never seen that frequency before. Oh, that's a new object. So you can see a lot of objects and even our human behavior actually demonstrates certain level of frequency. Okay, so that's become our signature, our ID, So that's why we lot of time computer scientists, when we do that, we don't recognize the frequency, but frequency is really a big deal. So we actually use wavelength analysis to actually get those frequency-based signature out. So that's basically some unique work that different from our work, from other work for cyber attack detection. And this slide just briefly show, like how we define, the wavelength model of attack data and norm data. So I won't get into the detail. This is actually show you how we use actually Q-score statistic there. Now, I guess there are too much detail there too, but I want to point out, like if you look at equation number 8 there, okay, and you see two, first is the bracket. Okay, you have yt minus fx. Everybody see that in equation 8? That part basically is subtract. The fx is the normal use model, it's the norm model, and yt is your observed data. So that part actually take effect of noise from your mixed data. And then the next times gx is your attack model. That's basically, so once you have y minus fx, that's basically suppose only the attack effect remain there. And you times the gx is multiply the effect of attack and make it basically make attack detection. So this actually based on the equation number 6, which assume, the attack and normal use have additive effect. Now, if you look at equation number 9, that's actually say, what if your attack and norm has multiplication effect rather than additive effect? And that's how you construct the Q statistic for the detection for attack norm separation. Just briefly some idea. And these two charts actually show you, basically you can see normally the Q-score, that's a plot of Q-score. Normally it fluctuates around 0 if there's no attack. But once there's attack, that Q-score actually either decrease from 0 or increase from 0. You can see that vertical line indicate when the attack happens. So it's clearly, give you clear indication when the attack happen, and you can detect that accurately. So that's something we can learn from our cyber detection work. Another technique I want to mention here, which I think have a really broad application, is what I call, that's what we are working on currently, it's called PartialValue Association discovery. So we know basically we have a lot of technique from data mining, statistical learning community. But if you look at all this technique, I think they have one major shortcoming. That shortcoming is basically most of the technique try to build a data model that cover all the value of data variables. Okay, so let's say that means you try to build the same model, or one model cover all the value of data variable. I gave you an example why it doesn't work that way. Because let's say if we talk about the physical system, there's relationship in the physical system. And usually we say those, physical, remember everybody heard about space crash, the crash, it's like there's an O-ring problem because the launch was happening during very cold weather. And O-ring actually feel that there's a leak, basically then the spacecraft actually erupt in the air. Everybody remember that? And you can see basically there are a lot of physical system objects. They follow certain relationship in the normal temperature. You go to another extreme temperature, the relationship change. The object doesn't behave this way. So that's an example, say, you may not have the same relationship for different value range of the variable. Everybody see the issue I'm talking about? So for example, let's say I'm looking for, the system performance relationship with the temperature. Okay. So, basically under the normal temperature, I may have a data model. Under extremely cold temperature, I may have a different data model. But if you try to build one data model cover both, basically normal temperature and the cold temperature, you will never find the fitted model. You will get a poor fit there, basically. So a lot of technique have that shortcoming. Okay, we say you better, basically, we need to have a technique that can actually detect we have different relationship for different subspace of data or for different range of data. Okay, so that's why we call it partial value association. So what we focus on is we want to separate, the data range you have one model, and data range you have a maybe different type of data model. So that's what this algorithm for. And there are 3 steps there. It basically step we try to actually, sometimes you have categorical data, numerical data, sometimes you only have numeric data. So we want to actually convert any numerical data into categorical data. That's step 1. And step 2, once you have all the categorical data, we actually develop what we call partial value association. So what association exists in certain subspace of data, or a certain value range of data. And step 3, once we find those partial value association, we try to generalize them, consolidate them. So even, let's say, you have same data model cover all value range of data during that step 3 consolidation generation, we can actually put a different association for different value range into just one data model, if that's true. Okay, so those are the few steps. And this show you actually some few technique we have. You can use how, let's say, if all your data are numerical data, how would you actually convert each numeric data variable into categorical data variable? And there's another approach, let's say, if you have, some variable are categorical, some variable are numerical, how would you use maybe categorical variable as a guide to transform those numerical data into categorical data? So that's the first step. And second step, we try to find those partial value association. Okay, so the association could be, means, we can actually give you association variable. I'll give you some example here. So this is actually the result we call associate network. And you say each arrow there, let's say if you see the dark line there, actually says AP hour is equal yes, and then lead to Fulton engineer extension. This is about engineer retention. So we try to find what factor make students stay in engineering, basically. So that's basically, you can see that's the variable, one conditional variable associated with another associated variable. Next chart here, you can see there's 2 variables. Let's say if you rate x36 equal to 1 to 5 and x7 equal to y, and lead to x4 equal to 0, that means those students do not stay in engineering after first year they enter the college. So that's actually gave you multiple variables association. So that can be very useful. Like if I go on to, basically if you talk about how this apply to the anomaly detection in finance, the key thing I think we need to work on is we need to develop, basically each transaction has multiple attribute variable. And the pattern we try to discover, let's say we try to determine what's the normal pattern of the user transaction. I think it's better to actually capture it using multiple variables interaction that are concurrent effect. So for example, I'm not too familiar with finance data, but I just gave very naive example. You say, if the transaction location is hometown, expense type is gas and fuel, dollar amount less than 100, that's normal. Okay, but you can see that norm activity need to be defined by multiple attributes rather than by one single attribute. I think that's the key. And the next example, I say, what is abnormal and uncommon? You can say if the transaction location is not hometown, expense type is gas and fuel, dollar amount greater than 100. So that's a combination of three factors that's not norm, could potentially be fraud. So this partial value association technique can be actually very useful to give you that multiple value correlation interaction effect, capture those and use those to define the norm and anomaly pattern. So I think that's the major point I want to make for my talk.